Hello, everyone. Good morning, and welcome to our virtual ICASSP tutorial on machine learning and wireless communications. I'm Yunina Eldar from the Weizmann Institute in Israel, and this tutorial will be delivered by Nir Schlesinger, my brilliant postdoc, who will soon be starting a faculty position at Ben-Gurion University in Israel, and Professor Vince Poor from Princeton, who all of you know and admire. Before we begin, we'd like to thank the organizers and the tutorial chairs, Sabrina and Philip, for inviting us to give this tutorial. Of course, we were very much looking forward to seeing you all in person in Barcelona and being able to have an interactive tutorial, but very thankful to everyone involved for giving us an opportunity to meet and exchange ideas, even under these difficult circumstances. This is, of course, the first time any of us are giving a virtual tutorial, and probably the first time you're participating in one. So we hope we still be able to do a good job in explaining the ideas and getting you excited about the potential of deep learning and wireless communication, which we really believe is an extremely important and exciting area and opportunity. Our focus in the tutorial today will be on the unique opportunities offered by the interplay between machine learning and wireless communications, where we're going to consider both the theoretical ideas and also show various applications to many interesting communication problems, which will hopefully demonstrate the many ways in which machine learning can help enhance the new generation of wireless networks. We're all aware of the fact that today, a very popular approach across all data science areas are ideas based on machine learning that learn the information needed from large amounts of training data. In fact, with enough data, deep networks tend to learn almost everything and have led to the best results in various tasks like image recognition, speech translation, and many other examples which don't have good models. Now, machine learning has a very rich history dating back at least to the early 40s, when McCullough and Pitts introduced the first mathematical model of a neural network in their landmark 1943 paper. In fact, the basic unit that they introduced in this paper is still the standard of reference for a mathematical description of a neuron, even in neural networks today. Now, moving ahead, in 1958, one of the first machine learning algorithms was developed by Rosenblatt, which is the well-known perceptron algorithm. And this is a method for supervised learning of binary classifiers, which is used today in many different applications, but was originally introduced for image recognition. Over the years, there were very many important developments in machine learning, leading to backpropagation and SVM in the 90s, and this really laid the foundation for modern deep learning. In terms of industry, the impact of deep learning began in the early 2000s when GPUs were developed and computers started becoming much faster and efficient at processing data. So this faster processing with GPUs processing pictures increased the computational speeds by at least 1,000 times over, for example, a 10-year span. And this led to neural networks being able to compete with other standard machine learning methods, such as support vector machines and a variety of other traditional approaches. By 2011, the speed of GPUs had increased so much that it already became obvious that deep learning had significant advantage in terms of efficiency and speed. One of the most well-known examples of the early success of deep networks is the famous AlexNet, which is a convolutional neural network that won several different international competitions in 2011 and 2012. So as we can see, in the past decade, deep learning has really revolutionized many fields with huge empirical success, especially areas where modeling is difficult and obtaining large training sets is actually feasible. Now, wireless communications also has a rich history and present. If we start by going back to the 40s, we already see early applications of commercial wireless telephone services. The first trials of cellular systems were conducted in the late 70s, with the 80s bringing commercial analog cellular technology with fully implemented standards. The real revolution in wireless began in the 90s with the advent of digital wireless networks and the introduction of GCM and roaming. This really led to a proliferation of commercial wireless technologies, such as cell phones, wireless computer networks, of course, the internet, navigation, email, music, and various different wireless connections for the laptop and handheld devices. The transition from analog to digital technology really enabled a substantial increase in voice traffic and of course the delivery of digital data, which is so important for all our modern applications like text messages, images, and various different types of streaming media. So looking back, the development from 1G to 4G and now into LTE and beyond to 5G really enabled many new and important technologies and accelerated the rate of advance. This, of course, comes with increased demands on speed, capacity, coverage, power efficiency, and costs, and leads to various system trade-offs that need to be optimized. So we've just very briefly seen the history and impact of two major technologies of the 21st century. Wireless technology on the one hand impacting the way we communicate, and machine learning on the other, which really has had a broad impact on many new technology areas. What we want to consider in this tutorial is where these two major driving forces of technology can combine and further accelerate future applications. So what we're going to focus on today are two main aspects. The first is how machine learning can be used to design and optimize communication networks, especially given the growing demands that we just talked about and the many trade-offs that have to be addressed in future networks, which lead to many system parameters that need to be designed and very complicated optimization problems. So we believe that machine learning can have a very important role here. The second aspect we want to address is how wireless networks can aid in learning by using the mobile devices as learning devices and harnessing the power of wireless communications to perform very efficient learning at the edge in a distributed fashion on the user device. So here we're going to use the wireless networks as a learning mechanism. So let's now go ahead and consider briefly these two aspects, which we're going to expand on throughout the tutorial. So first, let's talk briefly about how we can use machine learning to design wireless systems. Now, typically, when we think about standard signal processing and communication methods, they're typically designed based on models. So we're going to start with some physical model or a good approximation of a model, and we're going to use that to develop different optimal algorithms. This allows us to easily incorporate, for example, different domain knowledge and structure into the methods. So if we look at a standard wireless problem where we're going to assume some model for the transmitted data, the symbols here S, and then we're going to assume some model for the channel, which we're going to use at the receiver in order to design an optimal method to extract these bits that we transmitted from the received output denoted here by Y. So this standard approach heavily relies on our ability to estimate or approximate the various parts of the system, such as the channel and the noise model. Now, once the model is known or estimated, we can use it to develop various different optimal methods under different criteria, and we could also use the model to properly analyze the performance. So the advantage, of course, is that this leads to a very systematic way to design systems, and also often leads to methods that have controllable complexity. So to be a little bit more specific, we're typically going to start with a simplifying model to write down an input-output relation for a channel. So a common choice is, of course, the very well-known linear Gaussian model. In this model, we're going to assume that our received signal, which is denoted here by Y, is going to be some linear combination of the transmitted signal, denoted here by S, and H here is going to represent the channel. And to that, we're going to add some Gaussian noise. The problem is, of course, that this model may not be exact and it may not take into account various different channel distortions, which could be very difficult to model. The other difficulty is that in this approach, we're going to assume that the channel, which is represented by this matrix H, is known, which means that in practice, we have to accurately estimate it and track it when the channel changes, and this leads to a large overhead. In addition, besides the overhead, we're always going to have some tracking error, which can deteriorate performance and may be very hard to analyze. So this is exactly where we hope machine learning can help us. We know that machine learning does not rely on model knowledge, but rather learns it from the data directly, which would really help address the modeling issues. On the other hand, in communication systems, there's still a lot of known structure since many components of the system are designed by strict protocols, and many parts of the system can actually be accurately measured. So this leads to what we're going to call throughout the tutorial model-based deep learning, which are basically methods for combining learning with known models. And this is going to be an important theme throughout the tutorial today. So what this will enable us is to develop methods that on the one hand rely on structure when it's known, but on the other hand allow us to learn the unknown system parameters directly from the data. Let's now move on to the second aspect of the tutorial, which is using wireless networks to enable efficient distributed learning. One of the key components of deep networks is having available to us large labeled training sets. Now, very often, this data is coming from distributed users, such as images taken with a cellular device, data coming from smart vehicles, and data coming from different tablets. The training, of course, needs to take all these different sources of data into account. A standard way of doing that is for each user to send their data to a joint server and then perform training on the server using all the data. In practice, this is going to mean communicating the information over existing wireless networks. Now, this in turn is going to lead to several challenges. First of all, sending labeled data to a joint server requires very large capacity since the volumes of the data are going to be very large, especially when we're talking about images and movies. This also raises huge privacy concerns. As a user, we probably don't want to share our stored images with the server that others have access to. So what we can suggest as an alternative is that instead of doing the learning on the server, which will require all the individual users' data, we can attempt to do the learning at the edge, namely on the devices themselves. In this approach, each user is going to train a local deep network based on their local data without actually sharing the data. And what they're going to share across the network are only the learned weights or gradients of the network themselves. This leads to what is known as federated learning and distributed learning, where the data remains protected and local, and what is shared are only the network updates. Of course, this has to be done in a way in which the overall learning is still optimal and such that the shared data remains private. In this framework of federated learning, wireless communications are going to play a very important role since the wireless network is going to dictate the constraints and the opportunities for this joint learning. Now, there are many opportunities for wireless methods to help in learning at the edge, including, for example, various ways to ensure privacy of the information, techniques to schedule the users, ways to harness the properties of the channels themselves to enhance the learning process, and of course, channel knowledge to mitigate different interference over the network. Clearly, communication and coding methods are going to have a large role to play when the learning itself is done over a wireless network, and this is going to be the focus of the second part of the tutorial. So hopefully, this has given you a sense of the potential of merging wireless communication and deep learning, and outlined some of the main aspects that we hope to cover in the tutorial today. Before we go ahead and jump into the details, I want to end the introduction by stating some of our goals for the tutorial. So first, we hope to expose you to some of the exciting ideas and results in this area of model-based machine learning and see the way we can impact wireless system design and next-generation wireless systems. We also hope to provide a glimpse of the really huge potential of using communication tools for learning deep networks, which is an area that is just emerging and is sure to grow in the next few years. So what would we like from you? Well, we would have wished for this tutorial to be as interactive as possible, which of course is probably very difficult under the current circumstances, but we still hope over the break we'll be able to address various questions, and if not, then hopefully offline over email, we'd love to hear your input and thoughts. And most important, we hope that despite not being able to interact as much as we would like to, we hope you'll be able to learn and enjoy this tutorial. So with that, let me end this first part by going over the detailed tutorial plan. We began already with an overview of our goals and main topics. The next part will focus on relevant background in deep learning, which is needed for the rest of the tutorial. We'll then split the remaining of the tutorial into two parts, one that is focused on using machine learning to optimize wireless networks, and one that is focused on using wireless communication to implement distributed and federated learning. So with that, I'm going to turn over the tutorial to Nir, who's going to begin by giving an introduction to deep learning.
Hello, my name is Nir Schlesinger. I am a postdoctoral researcher in Weizmann Institute, where I have the honor of working with Yonina Eldar. In the next part of our tutorial, I will survey some relevant preliminaries in deep learning. As we know, we're nowadays witnessing the deep learning revolution. Deep neural networks allow to achieve superior performance in a multitude of areas, including computer vision, speech processing, and in various problems which are difficult to tackle using conventional optimization tools. What are those neural networks? In the end, those neural networks are a concatenation of a multitude of parameterized transformations. These are divided into affine mappings, such as fully connected layers, convolutional layers, and nonlinear activations, such as ReLU and sigmoid. And by concatenating a set of those affine mappings activation, affine mapping activation, we get an overall highly parameterized function which defines the network mapping. Now, in order to determine the quality of such a network, we need to define a loss function. It can be the logistic loss or the squared loss. And we want to tune the parameters of this neural network to minimize the loss. And we do that using training, using data. How do we train using data? The common tool is stochastic gradient descent or some variant of it. Now, how does stochastic gradient descent work? Stochastic gradient descent refers to the tuning of a set of parameters, theta, which dictate a function f of theta, which in our case, the parameters are the weights of the network, and f of theta is the mapping of the network. And it does so using training data and some empirical loss function, which is defined with respect to both the parameters and the training data. Now, the goal is to recover the parameters which minimize the empirical loss. Now, if the training data are randomized from some IID distribution, then it also coincides with the statistical loss. Namely, we can replace this sum here with an expectation with respect to the distribution of the training data. How can one tune the weights in light of the training data and the loss function? One way to do so is using conventional gradient descent, which operates iteratively, and at each iteration it takes the current weights and it reduces some learning rate or step size times the gradient computed at the current weights. Now, we know that this approach will end up converging to some local minima, which will hopefully be a good minima. However, when we look at the computation here, we note that computing the gradient at each iteration, at each training point, can be very computationally complex, given the fact that the training data can be very, very large. So what is usually done is what's called stochastic gradient descent, where instead of computing the full gradient, we're just randomizing a single training labeled sample, and we're computing the gradient with respect to this sample alone. This boils down to this equation here, which is much more computationally simple compared to the standard gradient descent, but it is carried out over a large number of iterations. Essentially, we call an epoch each passing over the complete data set, over the complete training set, and we train over multiple epochs. Namely, it's repeated a large number of iterations. We don't have to just take one sample at each time. What people usually do is use mini-batch stochastic gradient descent, in which instead of taking a single sample, we're taking a batch of samples at each iteration. Now, also, gradient descent on its own is usually not the algorithm used. Some variants of it are used, like stochastic gradient descent with momentum, like RMS-prop, Adam, and so on. But essentially, these are all variants of stochastic gradient descent meant to increase its convergence speed and to stabilize it. But the underlying rationale is quite similar for all those variants. Now, stochastic gradient descent deals with the need to take standard gradient descent and make it less complex by computing the gradient with respect to only a mini batch or even a single training sample at each iteration. Now, the question is, how are these gradients computed? Now, fortunately, while neural networks constitute complex mappings, which can imitate a very large number of different transformations, they have a specific structure, which is this concatenation of layers, or concatenation of parameterized affine mappings. And this format, this structure facilitates computation of the gradient because we can do that using the chain rule. In order to compute the gradient of the loss with respect to a given parameter, we just need to compute the loss with respect to the output of that specific layer times the gradient of this specific layer with respect to that specific element. And that makes the computation of the gradient relatively simple and can be carried out using what's called backpropagation. So stochastic gradient descent combined with backpropagation allows one to tune the overall weights in light of a loss function, an empirical loss function, do it in a computationally feasible manner, and those are two fundamental tools in training deep neural networks. Now, there are various types of models for machine learning and for deep neural networks. They can be divided from a broad perspective into the following. The first is the family of supervised training models, which learn a mapping from some input space to some label space. And this is carried out by providing the network with a very large number of labeled samples. Namely, here we're showing images, and we're showing for each image, we're specifying its label. For example, these are images of mugs, these are images of hats, and so on and so on. And by doing so, we should be able to tune the network transformation to be able to carry out classification or regression or any other of those supervised tasks. There's also the family of semi-supervised learning, which are quite similar to supervised, but they combine training using some label data, some data which we know to which label it belongs, and some data which we do not know to which label it belongs. And the other family of models is unsupervised learning. Now, unsupervised learning train on unlabeled data. Namely, we only see inputs. There's no label assigned to each one of those inputs. So obviously, we're not learning here a mapping from input to label. We're trying to learn something about the underlying structure, something about the statistics of those inputs, like how to compress them, how to generate samples, and so on. So let us now review some basic conventional machine learning architectures. The first is the classification network. Classification network operates on an input, which can take continuous values, and it's a supervised training, so it also has labels, typically taking discrete values, and the output of this network is a score. We are giving a score to each possible label given this input. For example, if our label space is cats and dogs, and we see a 32 times 32 color image which looks like this, then a desirable output of a network would be that it is 3% cat and 97% dog, for example. Now, the objective, in light of which such classification networks are trained, is what's called the empirical cross-entropy, or also the logistic loss, which is given by this expression here. And the main motivation for utilizing this, or at least the statistical motivation for doing so, is that when the empirical loss approaches the statistical loss, namely, we have a very large number of IID labeled samples, then the actual mapping which will minimize the resulting loss will be the true conditional distribution of the label given the input. Namely, we will be able to utilize the output of this classification layer to implement the maximum posterior probability detector, which is known to minimize the error rate, for example. Another family of networks is what's called regression networks. Now, the difference between regression networks and classification networks is that the output here is not a score. It's an estimate of the label. So the label can now take continuous values, not necessarily discrete, but this is also a supervised setup. As an example for a network which carries out an estimation task, we can consider the case where the label space is priced in dollars and our input are some attributes of a house, and want to predict the price of this house. Now, such networks are usually trained using the empirical squared error because, again, when the empirical loss coincides with the statistical loss, what we get is that the objective is minimized by the MMSE estimate. An additional family of machine learning methods are generative networks. Generative networks, unlike classification and regression networks, operate in an unsupervised manner. Namely, there's no label here. There are only inputs. And what we're trying to do is we're trying to learn a mapping from some known low-dimensional space into the input space. So, for example, A most common example is the generative adversarial networks, which, when properly trained, can map some random noise, whose distribution we know can be low dimensional, into an image of a celeb. So it essentially learns a mapping from random noise into the domain of celebrity images. Now, there are various objectives to design generative networks. They depend on the architecture. For example, in generative adversarial networks, we have a generative networks, we have a discriminator networks, which compete, and the goal is to optimize the min-max loss. There's also the family of variational autoencoders, which are trained using the elbow, the evidence lower bound. One can also utilize flow networks, where you can actually define the likelihood as the objective. But essentially, the bottom line is that generative networks attempt to learn a mapping from a low-dimensional known space into a desired high-dimensional space. The last family of established neural network architectures are autoencoders. Again, we are dealing here with unsupervised learning, namely, we only have sets of inputs. But here what we're trying to do is we're trying to learn how to recover the input from its compressed version. Namely, we're trying to simultaneously learn a mapping of this input into some low-dimensional latent space, and a mapping from this latent space back into the input space. And by doing so, we're able to recover some compressed version, or perhaps an approximate sufficient statistic of this input, from which it can be recovered with high accuracy. Now, the objectives here vary. It can be, for example, the squared error between the reconstruction and the input, while we are fixing here the dimensionality of the latent space in the middle. And in the end of the day, those autoencoders show great capability in learning low-dimensional approximate sufficient statistics without having to explicitly specify the distribution of the input, only to provide a large number of labeled data, of unlabeled data. These aforementioned machine learning architectures allow us nowadays to achieve unprecedented empirical success in various applications. For example, generative networks are now able to generate fake faces, to spawn fake people like the ones we see here. These are all AI spawned faces. Classification networks are now surpassing human performance in classification of images. However, this unprecedented empirical success does have its challenges and drawbacks. For example, in order to achieve that, we need a large training set, we need a large computational power, and we do not necessarily understand exactly what's going on, like we see here in this comic. In the end of the day, it may just boil down to throwing a large number of training set and doing some linear algebra without necessarily being able to interpret, to understand the operation of these neural networks. Furthermore, training time can now be substantial, as we can also see in this comic, which states that the number one data scientist excuse for slacking off is, well, my model is now training. There are obviously other challenges associated with deep networks, like robustness and generalization. And in this tutorial, which is about machine learning and wireless communication, we will try to focus on two main questions. First is, can we exploit the advantages and the benefits of machine learning tools while mitigating their challenges to allow them to optimize wireless networks? In addition, we will also attempt to answer the question, which of the challenges associated with machine learning can be tackled using communication methods?